Hi, in this video, I'll be going through more examples about discrete random variables, and I will first introduce to you the notion of variance. So variance, as its name suggests, you might have used it before in any conversation. It is the measure of how spread out our data is. So what does it mean by our data? It's just basically the values of our random variable. And so why do we want to consider variance is, even if we know the expectation, which is the average of the distribution, having the variance will be a good way of understanding how likely it is for the values, how near the values are from the mean or the average. And so really we want to consider the distance between a value occurring to its mean. And so we could have used the modular symbol for distance, but because this the absolute function is not differentiable at a point, we choose not to do that, and instead we want the distance to still be positive, and so we just use the squared function instead. And so the variance is just the expectation of x, meaning your value, minus away the mean, so it's how far it is already, and then you square it to make it positive. And as a result, you can prove that it is equal to also e of x squared minus the expectations squared. And really that's just a simple algebra, and I'll leave you to it to see the proof. And so by capturing how spread out your values are, and if you know the expectation, you roughly can visualize how the distribution will look like. Some certain properties of variance is that because it is a square of an expectation is the sum of this gx times probability of x equals to x, and this value is always positive, and since probability is always positive, when you sum them all up, it will still be positive. And so variance will be positive, which means that ex squared is larger or equals to ex whole thing squared. We also like to note that the variance of cx, so this is some constant c, is c squared times the variance of x, and you can just use this formula to prove it. And lastly, the following one isn't given in the over here, but the proof you can find in the textbook is that the variance of sum of two independent random variable is just the variance of x plus the variance of y. And if x and y are not independent, then the following case won't be equal. And we'll see it when we talk about covariance. And so the variance of x plus y equals to the variance of x plus the variance of y if and only if x and y are independent. And so let's take an example to show how we calculate variance. So x represents the outcome of a fair dice roll. We already know ex is 7/2, so we just calculate ex squared, which is 91/6. And as a result, the variance is ex squared minus ex whole thing squared. So it's just get 35/12. I hope this is clear. And we like to note that another form of measurement of a spread is known as the standard deviation, and that's just the square root of variance. So sometimes you use standard deviation, sometimes you use variance. It really depends on what a person wants. Lastly, let me just go through a few more common distributions for discrete random variable. And I won't show you the full range because there are so many, and there's like infinite number of many, but of course I'm going to show you some common ones that people use daily. The textbook has many more, so I urge you to read the textbook if you really want to have a good knowledge of what type of distributions there are out there. And so let's just say the first one is the Bernoulli's distribution, and that's what we already went through. What we want to say is that the expectation is just the probability p, and the variance is p bracket 1 minus p. And that's because it is the sum of 1 bracket p plus 0 bracket 1 minus p. And that is just p. And for variance is, you can work out and you'll see that it's p bracket 1 minus p. I hope this is clear, and we'll move on to some more interesting ones, and that is the binomial. And really the binomial, it will be represented as x following binomial, and n is the total number of trials, independent trials, and p is the probability of a success of a trial. And really the story is that you have n trials, you want to know, and x is capturing the number of successes. And so you can imagine 1 is your success, like the balloonie, and 0 is your failure. And so the first one you can have a success, second one you have a success, third one you have failure, fourth one you have a success, all the way, and then your total number of successes is k, and the total number of failures is n minus k as a result. And so you have k ones and n minus k zeros. And really these ones can be placed in any order, and so you need to choose or permute them in a way. So you need to choose out of the n trials, k of them to be successes, and for success to occur is probability of k, so it's probability of p, so it's p to the power of k, because you have p times p all the way to k, times 1 minus p n minus k. And that is the reason why the PMF is the following. I hope that is clear to you, and we'll move on. And so the expectation is NP, and the variance is NP times 1 minus P. And the reason for this is, well, you can work out the expectation from this formula. Let me just give you a proof which is very commonly used, is the use of this balloonie distribution. So really any of the n trials can be represented as x1, x2, and all the way to xn. And this each follows a balloonie distribution because it's either 1 or 0 as an outcome. And so the total number of outcomes is really the sum of the outcome of x1 plus the outcome of x2 plus all the way to xn. And so if you want to take the expectation of all this, it is really n times the expectation of xi, because all of them are equal expectation. And the expectation of xi is the expectation of balloonie, which is p, and that's why it's np. And that is the same reason for the variance, because the variance now is x1 plus all the way to xn. And because you know they are n independent, you can break them all up into variance of x1 plus the variance all the way to variance of xn. And each of these is p bracket 1 minus p. And so there's n of them, so it's np bracket 1 minus p. So really we now know the expectation of a binomial, the variance of a binomial. And so let's move on to another distribution known as the geometric distribution, where this time, instead of capturing the number of successes, we want to know what is the total number of trials before we reach our first success. So we let a random variable equal to the number of trials before the first success is reached, including the first success, basically. And so imagine you have all the way failures until you reach a success, and this occurs ith time. Well, so the first one must be a failure, so it's 1 minus p. Second one is also a failure, so it's 1 minus p, and it fails all the way to I minus 1 times. That's why it's 1 minus p times to the power of I minus 1. And then the last one is a success, so you just need p. So basically this is the PMF for a geometric distribution. And the reason why it's called geometric is the following result. Is that when you want to calculate the expectation and you sum the following, you make use of the geometric series to help you find the expectation. So when you sum this up, you can take out the p since it's a constant, so it's p sum of this whole thing. And this thing reduces to 1 over p squared. I'll leave it to you to read the textbook to see it. And as a result, the expectation is 1 over p. Similarly, the proof for the variance is in the textbook, and we like just to note that the variance is 1 minus p over p squared. And so the geometric distribution, in summary, has an expectation of 1 over p and a variance of 1 minus p over p squared. So I'm going through 3 types of distribution, and I hope this inspires you to read more distributions by yourself. I've come to the end of this video, and in the next video I'll start on continuous random variable, which is similar in conceptual understanding but to discrete, but there are some differences as well that we need to take note of. So I'll catch you in the next video. Thank you.